So, firstly, a very good evening and a very hearty welcome to all of you present here. We, Nakshatra, the Astronomy and Science Club of NIT Trichy, feel privileged to extend our warm welcome to all of you for presenting you with a series of guest lectures, Spectra, as an addition to our annual flagship event, Stardust.
I, Harshita, along with Vishwas, are delighted and honored to be your host for this session. To kickstart our Spacetime Odyssey, we have Dr. Hamsa Padmanabhan, scientific collaborator and principal investigator of the Swiss National Science Foundation at the University of Geneva, Switzerland. She's an international physicist, graduated from the Inter-University Center for Astronomy and Astrophysics, IUCAA, completing her PhD in physics with a phenomenal research expertise ranging from theoretical investigations in quantum field theory and relativity to data-intensive astronomy and astrophysics.
Her research focuses on unraveling the history of the universe. She explained that in the universe's beginning, there wasn't much dark energy, but the dark matter was more abundant. She plays an active role to probe both fundamental physics and cosmology, in which the HALO framework developed by her is used all across India, Europe, Canada, and the USA. We welcome Dr. Hamsa Padmanabhan to give her insight regarding Deciphering Cosmic Dawn, Mysteries from the Invisible Universe, and to share her knowledge and love of astrophysics and cosmology, followed by a small and informative talk for anyone interested in pursuing a career in this field.
Thank you, ma'am, for being kind enough to accept our invitation despite having a busy schedule. It is an immense pleasure to have you with us today. We request the audience to pose your queries at the end of the lecture. Over to you, ma'am.
Okay, thanks a lot. So first, thanks a lot for the very kind introduction and for the invitation. And it's great to see the nice work being done by your group at NITT. And it's really nice to also give this lecture at to people, to students here, and I hope that it will be sort of an introduction to what is going on, the recent trends in this field. So like you said, that I'm going to look at just some results in the fields of cosmology and astrophysics which are happening over the last few years and what would be projectable in the next decade. And especially this epoch known as Cosmic Dawn, which is essentially when the first stars and galaxies are supposed to have formed and lighted up the universe. So you can see some sort of cartoon picture here, but essentially there was a time when there were no stars and galaxies, and then we had this period. And most of it is not visible in the optical. So when we look at it from our eyes, we can't see that many of those epochs. So that's why it's like an invisible universe. But there are nevertheless many ways to probe these exciting epochs. Okay, so I thought I would start with a kind of broad introduction to the field, set the stage, and this may be familiar to many of you who are amateur astronomers and who are looking at the sky on a daily basis, for instance. So we'll start off with the landscape, right? A few sizes and distances which are of salient in the structure of the universe around us, yeah? So this is probably something familiar to many of the people who are stargazers. So we are somewhere here. This is the sun. We have our nearest neighbor star, Proxima Alpha Centauri. And many of these stars are identifiable in the night sky. So you can see, for example, the brightest one, Sirius here, and there are some other ones which you can see around the place. But just to say that this is for cosmologists, our backyard, sort of. It's the really small nearest neighbor kind of set of stars. And you'll see the scale. It's about 10 light years. So light year, as probably many of you know, is the distance that light travels in 1 year. And most of these are situated within this limit. And you'll see an arrow here which points to what is called the galactic center, so the center of our own Milky Way galaxy. And if you kind of zoom out and you look at it, and you look at the universe on a higher scale, you'll actually see our galaxy. Of course, this is not a photograph. This is somebody's reconstruction, because we couldn't go out and see that. But this is a fairly good representation. What is important to realize is that our galaxy, like many others, is a spiral galaxy. So you see that it has these beautiful arms. These arms are actually huge number of stars. And there are clusters of stars. So some of them are called globular clusters. The stars come together and they can form these objects. And there are the arms itself themselves have nice names. You can see some of the constellations and all, even as the names of the arms. What is very important to realize in this picture is that now the scale you see has changed. It is now something like 10,000 light years. So you think of it as a Google map kind of, and you'll see that this much is 10,000 light years. So we're talking about a big difference. And normally astronomers prefer to use a different unit, which is known as parsec and kiloparsec. It is similar to light year by a factor of 3, but it's more used in the technical terminology. So I've even put that for people here. And galaxies also have other small ones, dwarfs, etc., orbiting around, for instance. Our nearest neighbor galaxy is known as Andromeda. And this is, of course, a photo of it. And it's also a beautiful spiral galaxy. Something interesting is that between two galaxies, typically the distances are of the order of 1 million light years, 1 megaparsec kind of distance. That is indeed close to the one between us and our nearest neighbor. And you can see lots of smaller structures, clusters, galaxies across the landscape, even with this big galaxy in the center. So there are, again, groups. And today, I think many people here may have seen the beautiful images by the newly released James Webb Space Telescope. And these are older images from a ground-based telescope. But the story, which has been always the case, that galaxies come in wide number of shapes and colors and properties and characteristics. We have classified many of them. They help us to understand many properties of the universe. And many of these nearby galaxies are in about 10 million parsec, in that kind of 10 million light years away distances. And indeed, many more such are being available as we speak at much higher distances from space-based telescope like the James Webb. If you have, for example, more of a zoom out, you go higher. So you see here 100 million light years as your scale on the Google map. Then you see something even more interesting. You see that these galaxies themselves, they bunch together. So some of you may have heard of the Linaceae, the clusters and superclusters, for example. And they just bunch. For example, you have something called Centaurus, you have another supercluster, clusters and superclusters. These are just amalgamations, groups of galaxies which are loosely held together by their gravity. Between the clusters, you have empty spaces, and again, they also are named, called as voids in the literature. So the scale here again is really high. It is like about 100 million light years. And what is very important to which was a good confirmation of our cosmological principle and our theories of physics, which leads to our understanding of the universe, is that on the very largest scales, so look at the distances here, it's almost about 1,000 million light years. So 1,005. So it's 10 times more than the picture I showed you on the previous slide. On these scales, you see that the universe looks the same. There is no change. Each of these little points is a galaxy. This beautiful image is from a survey which just started in 2020 and released a huge amount of data, a 3D map of the cosmos, essentially known as the Dark Energy Spectroscopic Instrument. And you see that galaxies here are, they are more red, because I'll just come to that in the next slide. The light from them gets red shifted. And then here you see them more green, more blue, etc., which are closer. But what is interesting is that on homogeneous because it is uniform, and isotropic meaning it's looking the same in all directions. So that is true on the largest scales. It's not true on small scales, obviously, but in the largest cosmological scales, this is the picture, which has been beautifully confirmed even by the very latest surveys. It is probably fair to say that from these galaxies, the picture which emerges, what may be called the discovery of the 20th century is of course due to several people. They have it called the Hubble's law, but Slipher, Lemaitre, and various people contributed that you can popularly say the universe is expanding, but this is kind of a misleading statement. So precisely what one can say from the study of these galaxies is that as the distance from us to galaxy is increasing, the velocity by which it is going away from you also increases. So it is something like a balloon, you can think of it like that, which is kind of expanding. And in that, the distance between any two objects is increasing. So there, of course, different questions emerge, like where is it expanding into and so on. So those are not really the point here. Just that space itself is expanding, which means the distance between any 2 points keeps on increasing with time. And this is what is reflected in this graph. How do we know about this? We know about this because of elements. So many of you will have probably studied in your chemistry that you have elements which have spectra. So that's like the signature of an element. So it will absorb certain things, and looking at the spectra, you will see which element it is. Now, from these galaxies, the kind of things we get are always shifted to the red part of the spectrum, which is like telling you that there is something like a Doppler shift. So again, Doppler shift is not the right term because it is cosmology and you have to apply the general relativity and so on. But to a good approximation, it is enough to, it gives you the right answer for the lower distances, that the universe is behaving in a way that the galaxies are flying away from us. But this is true for every one of the galaxies. So there is no preferred center of the universe, for instance, that we are not at the center. Every place is also the center. There are three consequences of that previous statement, which immediately leap to the eye once you see that there is an expanding universe. Firstly, the universe has a past, because since it's an expanding universe, of course, it is not static. So it's previously there also is this use a steady state model that it used to be static, but I think we are almost certain from all the pieces of information that this is not true. It has a past. It was smaller in the past because it's expanding. And theoretically, one can show that the total amount of matter, more precisely matter energy, has been constant as the universe expands. So it was denser because that same energy matter was inside a smaller area. And denser things are usually hotter. So that actually applies even in the cosmological case. It was indeed hotter in the past. And what is fascinating is this last statement, that from our theoretical knowledge, we can actually describe or line out almost the entire history of the universe to an amazing degree of precision. So here is a brief history of the universe in one slide. This is like a nutshell. What is interesting is that the very first epoch, the very first instance really, we call it the Big Bang just for want of a term. We do not know what happened at the very first point. This word Big Bang is just a way of saying that we need to bring together the principles of quantum mechanics and gravity, which is an active area of research at the moment. But at this point, you have this quantum gravity, which certainly takes over as the main, the main player here. And so this is one part which is unknown. But what is interesting is all the way up to from 10 to the minus 32. So that's 1 divided by 1 followed by 32 zeros. That much of a second. Till today, you actually have a great understanding of the main physical processes which has happened in the universe. So for instance, around about seconds to minutes time scale, the light elements formed, that is hydrogen and helium and those kind of elements. And then you know exactly how the temperature of the universe was going. And at this one point, which is around 300,000 years, you have to read this over here, after the Big Bang, the radiation and matter separated. So whatever was before that was actually in the form of hot ionized plasma, protons, electrons. And this proton electron came together, became neutral hydrogen. And that is known as the epoch of recombination. So that's going to be important in what we'll look at later. So this epoch of recombination is when whatever radiation was there originally in the universe did not stay so coupled to the matter. So the matter and radiation sort of separated. And then came the epoch, which we are going to talk about a lot. The first stars, which is known as the cosmic dawn, somewhere around 1 billion years after the Big Bang. And the first galaxies, it started around a few 100 million years, went on around to about 1 billion. And what is very exciting is that this period is directly in the range of our telescopes today. So that is very exciting. And it's an era of direct observation. So therefore, you have this whole period of evolution of the universe, the broad picture of which we understand very well from our laws of physics. That is one of the big achievements of cosmology today, of astrophysics today, that we are able to understand. But several questions, of course, do remain in the context of the universe, which we need to think about. The first one, of course, is how exactly this process happened. How did these first galaxies form? I mean, what was the conditions like, and what kind of stars were there in those, etc. Second, an extremely popular question: are we alone? Are there other intelligent civilizations out there? And if so, how can we access, or can we access? And another very important question, the last one, is that we know this theory of general relativity, which is the one which was used to make all these predictions, which match beautifully, which has passed every test which was thrown at it. But does it work in all scenarios? Does it work in all situations and in all environments? So was Einstein right? That is kind of the last, another very big question. So the first one about the formation of structure actually goes back to that cosmic microwave background, the radiation I told you, which split from the matter at this very early time. It turns out that radiation has small fluctuations in it. So what does that mean? It means that the temperature of this radiation is not the same at all parts of the sky. So some parts it is slightly higher, and some parts it is slightly low. You know from standard thermodynamics that the temperature and density are very well related. So for example, what this radiation is telling you is that the matter at the very early universe was also less and more dense by a very small amount, 1 part in about 1 million, 1 part in about 100,000 at the very early time. But then you know that the force which is majorly affecting the universe is gravity. And cosmologists like to say that gravity kind of makes rich richer and poor poorer in some sense, because if there is a little bit of extra matter at a point, it will attract a lot of matter around it. And because of that, whichever place has less density in the beginning will actually become even less and less and less. So gravity makes things cluster. So things which are initially looking very homogeneous, if there is small amount of difference, if there is no difference, nothing will happen. But here there was small, and that leads to all the structure we see today, like all the galaxies and all these clusters, what I showed in the first few slides. So this is quite interesting, and it turns out you can use our current computing technology to actually predict how gravity acts. You see this initial picture of a universe which is something which people routinely do with computer simulations. They take initial conditions, which we know from observing that early radiation. We know sort of how the densities are looking like. You see it's almost homogeneous. You don't see much differences. But here is the movie will play. Just remember that this Z here is something like a time marker. So actually this is called redshift. It measures for you how old the universe is. So higher Z means earlier time. It is telling you about how the radiation, how much to the red it has shifted. Okay, so I hope you can see the movie playing. You'll see that the homogeneous structure has now clustered. So it'll keep playing. You see that as the universe goes on evolving, something which was initially homogeneous, if you allow gravity to act, it forms the clusters and superclusters, which we saw already in the previous slides, right? So by the time Z is equal to 0 is our present day. And so you see, this is how actually structure formation can be simulated on our machines. But we would like to do something more. We want to actually ask how we can observe this kind of process and what are the main features of it, for example, which are accessible. For that, we have to come to the universe's composition. So probably this picture also many of you are familiar with. It is a very humbling picture, which tells you that the kind of things which we understand and which we are made up of are only about 5% of the universe. The rest of the universe is in a material which we do not have an idea, which we have some kind of theories, but we don't have a laboratory understanding, known as, you can call it cosmological constant, or also as dark energy, that is behaving like a fluid which has a negative pressure, very exotic substance. People are still trying to understand. And yet another 27% is in the form of something called dark matter, which again is like the ordinary matter, but it doesn't interact with light. So it does, gravity is okay, but not light for this dark matter. And so only this much is familiar to us. And if this picture humbles you, then the next picture is even more humbling, which is that out of this 5%, the actual stars, the ones which we are really familiar with, the kind of things which this 5%, only 7% of that is in stars. And the rest, 93% of these baryons. So atoms in the universe, they are also called baryons. So interchangeably, I will use both of those. And the rest of this gas is actually the majority of the baryons. So if we want to understand the baryons, and you want to understand how did the galaxy form, we need to go to this gas. We are only a small part of it. This picture is true for the last 12 billion years. That has been the case of the universe. So stars have composed very little. The gas is the most. And what we understand today from our observations is that this baryonic universe, the baryons, mostly the gas, went through two major phase transitions. So first one is called as recombination. And that I told you about, which is when this neutral gas and radiation sort of parted company. And this happened when the universe was about 300,000 years old. And then came a period which is interesting, which is known as dark ages. So from this 300,000 all the way to about few hundred million, 200 to 500 million years, you had what is called that there was no radiation, there was no stars, there was only this cosmic microwave, that early radiation that was fading. And it was known most of the universe was filled with hydrogen because the hydrogen has become neutral. This came to an end around this time, about few hundred million, called first light. So that is called cosmic dawn, also called cosmic renaissance, to make a parallel to the medieval renaissance. And today, what is interesting is those first sources have ionized the radiation around, have put radiation to ionize the gas, and we see a highly re-ionized universe. So these are very exciting phase transitions of the universe, especially the second one, which is just about to be observed. So how did this reionization happen? So that is an important question in the study of cosmology. And the way it is, the way our observations and theory have shown us is that this is again an animation. You have an object which emits ultraviolet light, mostly a star galaxy. And that will create a bubble around it. So bubble meaning an ionized region. So you see there's a front essentially which keeps expanding, and that means it's creating more and more ionization around it. And these kind of bubbles expanded to fill the whole universe. So it's a very interesting process. So you see this for one of the objects over here, that it has a expanding bubble. But when and you see that, you know, all the neutral matter around it gets ionized. And what is interesting is that the entire universe was filled with these kind of luminous sources at different points. And in this movie, we will see the last one, what I showed you. This is repeated in the second slide, one of them. But in the left-hand side, you see many such objects. So if you have many of these stars, you'll see that all of them are creating their own little bubbles around them. And the time comes when these ionized zones just overlap. So that is what is known as the period of complete overlap or bubble overlap. And that period is when essentially the reionization is said to be complete. So what is very exciting is that the dark ages came to an end with the advent of the first stars. And these stars, and now you can see that previous thing has finished, and you can see on the left-hand side that all the bubbles are overlapping, and also they are getting hot. So the red one is the temperature. And at the end, you will find that all the gas has been sort of turned back into protons and electrons, which was how it was in the earliest time. So this is how reionization, again, these are all generated on simulations on the computers with theories, but it would of course be exciting and to actually see it happen. So it turns out that yes, we can do that, because as probably many of you also are aware, that cosmologists are a very lucky species because we can see the past. So of course, that is not at all a supernatural statement. It just happens because here it's a Zoom talk, but in general, if suppose we are standing I'm seeing somebody next door, then we are not seeing them exactly at this time, but slightly older version, because light takes a small amount of time to reach us from that thing or person. And that means that if you are having something very far in space, then you're actually seeing that at when it was much in a much earlier time. And today our telescopes are such that they can show us images of objects which are situated even a few 100 million, when the universe was a few 100 million years old. So that's almost 13 billion years in the past. So we are able to, for example, with the James Webb, see light coming from a very early time in the universe. And that is how we are actually observing, as we speak, the first galaxies. So we observe light from their very early times, and from when they even formed. And we can, for example, also go and see dark ages like this. One of the techniques by which we see the process, especially of reionization and this cosmic dawn, is by using something called quasars. The quasars are, you can think of them as just torchlights. They are certain types of galaxies which are active in nature. And what you see is that at a very early time, Z again tells you the universe is about 1/7 of its present size. At that time, if you have this point source, as light from that quasar comes to us, it gets modified. So for example, if there is hydrogen between us and the quasar, and there are some galaxies, for example, then the light gets absorbed by these things. And what comes at the end will be a tracer of whatever lies between you and that object. So for example, when you have this process of reionization, then you see that the light from this quasar, this is just a cartoon, will go through a huge period which is neutral and then ionized. So the light is changed in a very specific way, and the light has inside it encoded that the universe was neutral and then became ionized. More of hydrogen, then more of absorption, typically, of the ultraviolet light. And that is why we can show from these studies that the reionization happened at a particular time. And what is happening today is more exciting, that there is a promising probe of the early universe in the radio part of the spectrum. So I think most of you must be familiar with the megahertz radio waves. So for example, their wavelength is in a few centimeter, few 10 centimeter. And radio waves are very useful to understand cosmology and understand the early universe. This is because just as we get terrestrial signals, and we are familiar with that in this radio regime of megahertz, etc., even celestial objects, especially the hydrogen, for example, will send emission in the radio spectrum. And this radio light comes to our radio telescopes and can get recorded. And what is also very interesting is interesting fact that if you are having an analog TV, an old one, then some of the things which are coming in the signal is actually the cosmic microwave background, which is a small part of it, but that is coming from the extremely early primordial universe. So you may even get it on an analog TV. But what is quite interesting is that the hydrogen, which I told you is most common in the universe and is definitely a large amount of it in the dark ages and in the just before the cosmic dawn. So we have a transition of hydrogen. This probably some of you are familiar with. This is called the 21 centimeter transition. Hydrogen atom essentially has it has a proton and an electron. And one of the energy state is when the spin of the proton electron are parallel versus anti-parallel. So when the electron, when you have these two energy levels, and you have a sort of jump from the higher to the lower energy state, then the wavelength which is emitted is of a characteristic length, which is 21 centimeter, which lies exactly in the radio band. And this transition is extremely forbidden, so you can't see it around us in the laboratory, but you can definitely see it in the cosmos, because there is so much of hydrogen there that you can see this transition, and you can see the hydrogen emitting in this 21 centimeter. For example, our own galaxy has been imaged in this routinely, and other galaxies as well, in the 21 centimeter. And you'll see here a map. This tells you a bit, this essentially is a line which tells you the density of the hydrogen, and this tells you where, where as a function of the map, where as a function of the space in the galaxy it is located. And if you were lucky enough to see in the radio wavelength, you will see a very bizarre universe. So this is something somebody has put together. You can see a night sky which looks very, very different. There can be jets coming from those quasars, which I told you about, and even aeroplane jets you can see at radio frequencies. And if you see other galaxies in radio, so you see this is where, of course, the radio waves lie. The optical galaxy, what you can see with the eye is just this much. But at the same scale, if you see in the 21 centimeter galaxy, you see a much bigger one. So you see a large extended hydrogen region. So just telling you that the hydrogen gas is very extended. And when you look at reionization from this angle, in fact, a large number of efforts around the world are probing reionization using this radio spectrum, using this 21 centimeter line, including, of course, our GMRT in India, and there is another effort in the Netherlands, South Africa, and other telescopes. Many of them are very extensive, big telescopes like the ones I showed you, but large arrays of those telescopes, because you need a lot of sensitivity. And one of the biggest ventures, probably the biggest one, is called Square Kilometre Array, SKA, coming up in South Africa and Australia. This is an international venture. Many countries are observers of being part of it, including India and Switzerland as well. And it should be operational in a few years. There is 1 square kilometer of collecting area, and it will probe for us the epoch of the first galaxies. So this is the Square Kilometre Array. Its dimensions are very extensive. As you can see that with such a big telescope, You have huge number of, so you can go to the website and look at its specifications, 126 tennis courts. This is the kind of number. They have already started construction a couple of years ago, and they are on their way to getting themselves set up in both of these places. And these are some facts that you will need a large number of years to play back even one day of data of this telescope. It's really huge. It's a big data venture. And it will generate about 11 exabytes. This is a word which I learned about a year ago, because apparently 5 exabytes is all the words which all human beings on this planet have ever spoken. So it will generate twice that every single day. So it's a huge amount of information. And there is huge more data in the daily network than entire internet, probably also 2021, I don't know. But this is really a big venture. And the reason for that is because it's trying to probe a very small signal from the early universe in the 21 centimeter. And why it's important, yeah? One of the main reason is that in this 21 centimeter, there is a new technique, which has come to the fore in the last decade, and it will happen also in the next few years, known as intensity mapping. So this video, which will play, will show you a glimpse of that. So what you do is you go and look at a galaxy, for example, and you map the intensity of the hydrogen. So you saw in that previous plot that galaxies have a lot of hydrogen, especially in the outskirts. That is emitting in 21 centimeter in the gas. And this emission is coming all the way from whichever galaxies are there towards our telescope. And it will, of course, be shifted towards the red, depending on where the galaxy is. And you can make a map of whatever exists at that frequency. So 21 centimeter won't look at 21 centimeter anymore. It would be slightly shifted to the red. And then if you have something which is at a different epoch, you will have it, again, you can make a map at that epoch, and so on and so forth, all the way until almost the present. So intensity mapping offers a way by which you can actually map this gas across different periods of the universe. So you can see the universe evolving in this hydrogen. So that is why it's very exciting. And indeed, you can see a 3-dimensional universe. So what is this called is that is people here who are familiar with the medical field will probably know about tomography, PET scan, which is positron emission tomography. So tomography essentially means like a 3-dimensional view. And you can do that in 21 centimeter because every frequency is a different epoch. So each frequency which you get in your channels will show you a different period. And that's why you can build up this picture. What you can realize is that our galaxy survey, even the one I showed you in the first slide, reaches only up to a very small part of the observable universe. And even including CMB, you will be able to get about 10,000 times more amount of information from this 21 centimeter. So it's huge. We're actually going to access almost the whole universe in our baryons. This is another interesting picture that I showed you, those bubbles and the gas and those bubble overlap. In 21 centimeter, you can actually access that because you're seeing the universe as it was at different times. And because of that, you can see different epochs, because at different wavelengths, you're seeing the universe, you're seeing the same 2-dimensional structure. You can see the bubbles, you can see their overlap in this technique. One of the things which we have been working on has been this Halo model framework, which is essentially a way by which you combine today's observations of 21 centimeter as well as other observations of hydrogen to bring together a comprehensive view of neutral hydrogen all the way up to almost the epoch of reionization. And that is very useful because it helps us to make predictions for what the Square Kilometre Array and other things will see. So we make predictions for the telescope. One of the things which is very important here, of course, is that it's not very easy to observe it, because that's why you need very sensitive telescopes. This signal, which is the cosmological signal which you want to detect, is sitting behind a large number of unwanted, so to speak, for the cosmology signals. There are point sources which are much brighter. There is our own galaxy which emits in this regime. And there is also our mobile phones and different terrestrial kind of interference. Totally, the interference goes up to almost 5 orders of magnitude. So about 10 to the power 5 times more noise compared to below which you have to extract the signal. So it's challenging, but there are ways by which we can get down this challenge and get to the signal. One of the interesting ways, which was, so for example, one of the things which was actually claimed to have a first detection, this happened around about 5 years ago, 2018. And what they did was to use a telescope, very simple structured telescope known as EDGES. And they found that they probably get a signal. So this is something like an absorption signal of hydrogen. And you can see the redshift. So redshift about 1819 is somewhere around a few 100 million years. So few 100 million years after the Big Bang, they're able to observe hydrogen. But the only thing was that maybe there are some instrument features. People have been talking about that because of all those things I told you, the foreground and instrument and so on, that maybe people had a concern that it could be an instrumental effect. A team which was actually led out of India, known as the SARAS-3 experiment, repeated this with a different configuration, which was placed on a lake. And it was placed on a lake because it helped to mitigate the interference in a very interesting way, which was possibly there in the previous one. And what they found was they were not finding evidence of it. So just suffice to say that it's very exciting. This happened just less than a year ago. It was 28 February 2022. And possibly this could be, and then more experiments will either confirm or rule out this. In any case, it's very exciting because we could have seen probably the hints of the first stars, cosmic dawn. One of the ways in which you can actually mitigate this foreground is known as synergy. So that's something which I'll spend a little bit of time on because that is one of the things which we have been looking at also in the context of Halo model. Synergies means that you use the 21 centimeter along with a different tracer, a different observation. So for example, you have James Webb Space Telescope, which actually had put out these very nice images of the glass galaxies. Probably people have seen this. These are the furthest galaxies ever detected. They were born and they are being, the light from them is coming 200 million years after the Big Bang. It's really far. Now, these galaxies and other galaxies, if you have a galaxy survey on top of 21 centimeter, then it can be shown that you actually do very well with terms of foreground because the foregrounds are not common. So they kind of cancel out in the analysis. So that's why it's important to have synergies. And other synergies are some of the sub-millimeters. So probably some of you have heard of this, microwave transitions. So for example, there are molecules which have rotational energy state. And also there are ionized species which emit in gigahertz frequencies. Those ones are very important tracers of star formation. So up to where they exist, if you combine them with the 21 centimeter surveys, then also you can cleanly probe the signal without being affected by the fog. You can use this now. I'll just spend a few minutes to answer some of these big questions, which I indicated. First one is, I told you that up to that 10 to the minus 32 second, you still don't know what happened. Turns out, of course, there are theories for it. One of the main theories is called inflation, which is believed to have led to the structure formation because of those small fluctuations were generated then. And there's a particular parameter, so you don't have to go into details of it, but parameter called non-Gaussianity. So this non-Gaussianity is a quantity that measures the deviation from, for example, a Gaussian initial condition. So those first fluctuations which I showed you, what kind of distribution they have. And if this number is very large, then you'll get very weird universes. So actually, this number is close to zero. And what most of the experiments are consistent with that. but you can use the 21 centimeter survey to measure this number and see whether it is consistent with what the other surveys are giving. What is interesting, which we found by using this halo model and so on, is that you don't have to worry about astrophysics when you measure this quantity. So the astrophysics doesn't interfere much with it. So that's very good news for the first telescopes, these telescopes which are going to measure the signal. The other one is, of course, this 28%, what is dark matter made of, for example? One of the prime candidates is known as axion. The axion is something which is many of the extension to the standard model of particle physics, which you may have heard of, has this particle. And you see some of this is actually nice, beautiful pictures of what could be the dark matter distribution inferred from its gravitational effect. So this is not actually the light, this is a false color image of the dark matter. What is interesting is if you combine the Square Kilometre Array and another survey which probes the cosmic microwave background, you can actually get very good constraints on this dark matter candidate. So again, that's very exciting, one of the big questions. And of course, modifications of gravity. So for example, people have also postulated that the modified gravity can explain this late time universe, this major fraction dark energy, which we are not yet familiar with. If this is true, then the Square Kilometre Array play a major role in constraining such theories. And we did some work where we looked at how we can do that with not just with SK, but also its previous precursors, smaller experiments. And we can also do testing gravity under very extreme conditions like black holes and so on with the Square Kilometre Array. And of course, finally, the very interesting question of, are we alone? It turns out that these radio experiments can even throw some light on that, because what is known as the cradle of life in the exoplanetary regime, called as dust. Normally, when you have stars, there is a dust around them, and that's a disk where the planets usually form. And those ones are actually detectable at high frequencies. People have found that the Square Kilometre Array can detect radio signals if someone is broadcasting a television even dozens of light years away, we will be able to detect it with the Square Kilometre Array. So that's it. So let me conclude by just telling you that today we are able to observe the furthest and earliest galaxies. And it's very interesting because our telescopes are good enough to allow us the sensitivity for that. Not just the optical ones, but the radio telescopes are able to observe this invisible universe, and they can go up to this cosmic dawn, for example, where there is a lot of neutral hydrogen. And especially the Square Kilometre Array will be a big player in this game. It will be coming up over the next 10 years or so. And it's very important, as we point out also, to understand the distribution of neutral hydrogen, and especially its 21 centimeter emission, and to synergize, to combine these observations with other interesting constraints, other interesting data to avoid challenges. And if we can do that, then the next few decades promise to answer some very big cosmological questions. Thanks a lot. I'll stop here and be happy to take questions.
Yeah. Thank you for that insightful and informative lecture, ma'am. You have surely enlightened us with and our audience with such an amazing